So no doubt you've been a passenger in a car, sitting in the right seat or to the right of the driver when the driver makes a left turn. And you probably have had that sensation where as the car's turning quickly left, you think that you're moving towards the right at the side of the car. Well, in fact, what's happening is the car is moving left and you have a tendency to go straight. So what happens is the door, the right door of the car, pushes on your right shoulder, forcing you to move with the car. So here's a diagram of just that, where the red box represents you as the passenger making that left turn with the radius of r. Here's the center of the circle, the positive. And if we were to draw a free body diagram, we know that there are three forces acting on you. There are two forces in the vertical, and then there's the force of the door forcing you to move with the car. So if we analyze the free body diagram in the y direction, we have Newton's second law, the general statement. F net is equal to ma in the y direction. We have two forces in the y direction, Fn and mg. So Fn minus mg is equal to m times 0. The reason that's 0 is because you are always on the seat of that car. You're not moving above the seat, nor are you moving below the seat. So what that means is that the normal force provided by the seat pushing you up is countered by the gravity pushing you down. Actually, I guess it would be the other way around. The gravity which is pulling you down is countered by the upward force of the seat. Now in the x direction, Newton's second law again, F is equal to ma. We need a centripetal force to cause an object to move in a circle. So the net force is equal to the centripetal force. Centripetal force is equal to mass times centripetal acceleration. And in this case, the centripetal force is provided by the force of the door, so Fd, and that's equal to mv squared divided by r. So what do we feel? We feel Fd, the force of the door, pushing you inward. That's the centripetal force. And if the door was missing, the passenger would just fall out and travel tangent to the circular path. So instead of moving and continuing to move left, if the door, let's say, flew off the car right at this point, then the passenger, you as a passenger, would just keep moving in a straight line, perpendicular to that centripetal force. The last example we're going to look at is something we find in an amusement park called the Rotor Ride, which is essentially a large spinning room. And in a Rotor Ride, what passengers do, or riders do, is they stand prone right up against the wall, their back pushed up against the wall, and that entire room begins to spin in a circle. It begins slowly and gets faster and faster. So what happens as the ride progresses, the ride spins fast. Once it's spinning fast, you have this sensation of being thrown outward, where in effect what's happening is the wall is actually forcing you to travel with it in a circle, so you feel the push of the wall on your back. You just interpret that as being thrown outwards. So you feel pushed against the wall, the floor drops, and when the floor drops, there's enough friction between you and the wall to prevent you from sliding downwards. And that's because of the normal force provided by the wall. You do recall that if you push on the wall, or you push on a surface, the surface will push back on you with the same force. And that's what's going on inside the Rotor Ride. So if we analyze the free body diagram, there are three forces. Your weight, of course, being pulled downward. We have the force of the wall going towards the center of the circle. Now that's a surface, so instead of calling it F wall, we're going to call that a normal force, because that's what it is. It's the force of the wall surface pushing inward. And perpendicular to that, we have the force of friction. Friction and normal forces are always perpendicular to one another. So that emphasizes that upward force is in fact the friction force. Usually we see friction forces along horizontal surfaces. Here's an example of a friction force on a vertical surface. So if we analyze the forces, Newton's second law is equal to ma. The two vertical forces, Ff minus mg, is equal to 0. So that means that the force of friction is equal to mg. In fact, to prevent you from sliding down the wall, Ff has to be either equal to mg or greater. It could be greater if the coefficient of friction is large. This is a limit. We have to have at least enough friction to prevent sliding. If we have more friction, great. We can actually end up spinning the ride even faster. So if we continue on here, Ff is equal to mg, but we know Ff is equal to mu Fn. That's the friction formula. So we do a substitution here. And if we rearrange this, the normal force, which is the force provided by the wall, is equal to mg divided by mu, the coefficient of friction. If we further analyze this, in the x direction, F net is equal to ma, Newton's second law. The net force provides the centripetal force, and that's equal to mass times the centripetal acceleration. We said earlier that the centripetal force is provided by the normal force of the wall, and we also said that the normal force is equal to mg divided by mu. So we can do two substitutions in sequence here. Replace the Fn with mg over mu, and then we have this statement, and you can see that we can cross off the masses from either side. So mass actually doesn't matter. It doesn't matter how large or small your body is. You will have the same effect in terms of how fast the ride can travel for you to stick to the wall. So in the final form of the equation, V is equal to the square root of Rg divided by mu. And notice again, mass does not matter.